Swayam Prabha. Digital India. Educated India.
Our second presenter is also from IIT, but different IIT, Indian Institute of Technology, Kharagpur. And this paper will talk about something called sonor crystallizations of plate-like polymorph of pyrazidamide. All right. So this is a paper from IIT Kharagpur, and Dr. Sankar, is that Dr. Saka, will be presenting this work on behalf of his co-worker. The floor is yours.
Good morning, everyone. Myself, Abhishek Marana. I'm from IIT Kharagpur, and I'm working on multidimensional population balance modeling in the crystallization processes. So today, first of all, I will be talking about your major use of crystallization processes in pharmaceutical industries. As we have already talked about, the pharmaceutical industries is a billion-dollar industry in which the market share of Indian pharmaceutical industries is around 2%, and it is substantially growing over the period of year. Now, every pharmaceutical industries has one unit operation as crystallization process, which is generally used for purification, downstream processing, or increasing the bioavailability or dissolution properties, and especially for particle engineering. Now, in particle engineering, recently sonocrystallization has gained interest because it can be used to affect the properties of crystals form. Now, there are different modes of sonocrystallization, such as we can vary the amplitude of the ultrasound, or we can vary the frequency of the ultrasound. Now, for our case, we'll be using amplitude variation, and with that, we'll be controlling crystal size distribution and process intensification. Now, in an ultrasound, what happens is cavitation bubbles are formed. Now, these cavitation bubbles increases the nucleation rate, decreases the particle size, and here you can see in particle engineering different ways of ultrasound insonation by which the crystal size can vary. Now, so our target is to use ultrasound, or you can in crystallization or sonocrystallization. Now, our target solute is pyrazidamide, which is generally used as an anti-tuberculosis drug, and it has 4 polymorphic forms, namely alpha, beta, delta, and gamma, among which alpha is the most stable at room temperature, and the dissolution rate, in dissolution rate, gamma is highest. So the commercially available alpha form is generally forms a mesh-like structure. So it causes difficulties in pharmaceutical industries like poor flowability and downstream processing. So here you can see the filtered alpha form, it has formed a mesh-like structure, and here we have the FSM image. So the next stable form is the delta form, which is a plate type form. Now again, it has same dissolution rate as alpha form, and here we can see the optical as well as FSM images of that. Now, several studies have been done to crystallize delta form, namely cooling crystallization, anti-solvent crystallization, polymer solvent induced crystallization. So now our target is to do a sonocrystallization to obtain this delta form and do a multidimensional modeling. Okay, so for our model development, we have taken pyrazidamide, and the solvent used is dioxane, and we have used 4 amplitudes: 10%, 20%, 30%, and 50%. And 2 cooling rates are used, 18 and 30, and temperature range is 50 to 20 degrees Celsius. We are cooling from 50 to 20 degrees Celsius. Now, for this is the experimental plan. We have induced ultrasound for different length of the process, and we have tried to model it. Now, in the modeling, so here we have the FSM images. So here you can see, as the amplitude is increasing, the size of the crystal particles formed is decreasing, and this is for half of the process. If you are if you are giving ultrasound till the end of the process, the particles are even getting more smaller, and with 30% and 50%, it is forming agglomerate. Now, similar case for this is the XRD data. Now, similar case is for another cooling rate, 30 Kelvin per hour. Same thing is being been seen. Now, here you can see for 30% and 50%, the particles formed are so small and agglomerated that it is difficult to segregate. We can't confirm that it's a plate-like structure. So for our model, we have taken 10% and 20% amplitude for model design. Now, for model design, we need a size distribution. So size distribution is done by image analysis, and the concentration measurement is done by UV spectrophotometer, in which this is the calibration curve. Now, coming to the modeling part. Now, we have done a multi-dimensional. When we say multi-dimensional, it means the particles have different dimensions. Now, for our case, we have 2 dimensions. Now, see here, you can see the plate-like structure, you have distinctive length and width. Now, there is also thickness, but the thickness of the particles seems to be constant, which is 10 micrometer, which is we have analyzed using FSM analysis. Now, next, this is for model development, we use the population balance equation. Here in the population balance equation, we have X is a state vector which represents the internal and external coordinates of the crystals in a system, and V external and V internal are the transport velocity for internal and external coordinates. B and D are the birth and growth of particles, and the birth can be due to nucleation or breakage of particles, and death can be due to agglomeration, dissolution, or breakage. Now, for a homogeneous batch process, V external can be dropped, and we have only V internal. So for a 2-dimensional system, we get a equation as this, where GL and GW are the growth rate along length and width. These are the kinetics, nucleation and growth kinetics that we have used, along with mass balance. So here in the growth rate, you can see G, W, and GL. They are the growth rate along width and length. And we have 2 nucleation rate, J, US, and J prime. Now, J US is implemented when the ultrasound is on, and J prime is used for silent case, or we can say that when ultrasound is not there. Now, to implement breakage, we have a function where S is the selection function, B is the breakage function, and here this is for the death. We have another function that is death due to ultrasound. Okay, so now to implement breakage, now here you can see a plate-like structure. So when the ultrasound is applied, a particle having a rectangular plate-like structure can break any point in between the mid plane. So we have considered that it is breaking within 30% to 70% of the plate, and we also assume that when particles with length less than 20 micrometer does not break, because that we have observed from a analysis. Now, here we have F total, that is the frequency of stressing events, and this is the breaking distribution function. Now, what happens here is, now suppose this is a particle, and here we have a length L dash and W dash. Now, when suppose it breaks at this point, now the new particles formed. Now, suppose for this the length and width is interchanged. Now, for this the length becomes the W dash, or you can say the width of the original particle, and the width becomes an AL at a point where the breakage is happening. Now, this interchange of particles, particle length and width, should be taken into consideration, and we have taken that in breakage distribution function. Now, solving a population balance equation, we have generally 3 methods: discretization, movements, or stochastic method. Now, each have their advantages and disadvantages. Now, that I will not go into details. So for our case, we will be using discretization method and stochastic method. We will be using high resolution discretization method and event driven constant volume Monte Carlo method. Now for high resolution discretization method, the population balance equation, which is an integral hyperbolic equation, we have solved it by discretizing. We have discretized the length and width across in n cross n matrices, with delta and delta w being the step size. Now we got a reformed PV equation as this, and here this equation is further modified with upwind scheme using piecewise polynomial interpolation, and we got it. Now for Monte Carlo method, we have two types: time driven and event driven. Now time driven is like we'll be assigning the time step and then implementing the all events. Now here events can be nucleation, growth, breakage, agglomeration. Now the problem with time driven is there is no guarantee that event may occur, and this can lead to a decrease in simulation speed. But for event driven, there is assurance that the event will take place and the simulation gets faster. Now again, Monte Carlo is further divided into constant volume and constant number. For constant volume, with increase in time, the volume remains constant, but the number of particles in the system may increase or decrease. But for constant number, the volume may increase and decrease and the number of particles remain same. Now for constant number are generally used in the literature for the seeded crystallization, where we put some seed and we use growth rates, different population balance equation for that. But for our case, we have unseeded batch crystallization, so we will be using constant volume, and for faster simulation speed, we will be using event driven. So our model becomes event driven constant volume Monte Carlo. So how the Monte Carlo algorithm takes place? Now suppose we have a homogeneous, there is no solid present in the system. Now for that case, the p nucleation or the probability of nucleation is greater than 0, means there is particles will be forming, so probability will be greater than 0, but there will be no probability of breakage and growth, because no particle is there, so there will be no growth or there will be no breakage. Now next, once the particle is formed, the probability of growth becomes greater than 0, and there will be nucleation and breakage become it's still 0. Now once the particle grows to an appreciable size, then the probability of breakage becomes greater than 0, and this too becomes 0. And this is how the algorithm proceeds. Now for this is the flowchart for the high resolution discretization method. Here we have one factor. It will check whether the particles is greater than 10 micrometer. Unless it will keep on growing, and once it reaches 20 micrometer, the particles breaks by the functions that we have used. Now for Monte Carlo also we have done the same. Here we have we have used the nucleation frequency as nucleation rate into volume of the system. F growth is taken as this, and the probability of nucleation and growth and breakage are taken as this. Now this Monte Carlo model is used to validate one-dimensional crystallization, where we see it's perfectly matching with the system. As you can see, this is a concentration profile. Here you can see the experimental high resolution discretization method and the constant volume Monte Carlo models all fits perfectly well for concentration as well as CST. And this is the nucleation rate. Here in the nucleation rate, you can see there is an increase in nucleation rate for increase in ultrasound amplitude. And this is the model validation. We have taken two different set of experiments to validate our model. Also perfectly matches all the profile, concentration and CST. Now here we have how the ultrasound amplitude impact the concentration profile and CST profile. Here you can see the increase in ultrasound amplitude, the nucleation takes place faster, as well as the particle size is decreased. So coming to conclusion, this model based on batch sonocrystallization can be extended to continuous crystallization, and this can be used for optimization and control process, as well as this can be extended to include agglomeration also. So these are my references. Thank you.
Thanks to the speaker for keeping on time. Thanks. Appreciate it. I'd like to open the floor for Q&A. We have you have maybe a few minutes for question and answer. We can have 1 to 2 short questions. Okay, you have like to ask the questions? Okay, please introduce yourself before you ask.
Very nice presentation, Professor. So I'm Harman from Shell, and I'm working with a group that's very focused in process systems engineering. So my question is, your purpose of sonication is more homogenization and control of the particle size, right? Okay. And the elegance, so you've compared 3 different techniques of solving your population basic. Okay. So which of the 2 in specifics you chose specific scenarios, which of those 2 techniques perform better?
So yeah, that's a good question. Actually, both have their advantage and disadvantage. In terms of computational time taken, Monte Carlo takes more time to solve a system than hybrid discretization method. But the thing is, the number of particles in a system due to numerical discrepancies, or you can say, the number of particles increases or decreases for discretization method. But for a Monte Carlo system, it remains same. No, that means there is all conservation of mass, number of particles. It is following all things. But only one demerit for Monte Carlo is the timing. If we compare, it is like around 50 times more than discretization method. But it gives accurate result, more accurate result, and it can apply. It is easy to apply it for complex systems. Basically.
Okay, and robustness perspective.
So robustness, actually, we haven't checked, but we can try for that.
Thank you.
Thank you. Let's thank the speaker again. Yep. You can continue the interaction offline. Thank you.